Hello, everybody. This is the fifth lab of our Physics 20 to 11 class, and it is the Create Your Own Adventure. And today I will be talking about the falling Slinky problem. So the introduction, basically the purpose of this lab is to predict what will happen to the bottom of a slinky as it is released from rest at the top. So what we're going to be doing is we're going to be observing a real life video of a slinky being dropped from the top with tracker, with the video that is provided. And then we're going to be observing a glow script model that models that real life model. And then we're going to be comparing them. In the end, we're going to be seeing how there are equal and opposite forces working on objects, which kind of creates some seemingly impossible things to happen, like almost magic. So some of the applied ideas inside of this physics problem is the net force equation, where mass times acceleration equals a change in momentum over time, which kind of translates to the velocity update and position update equations, as shown. And then there's also going to be a drag force equation we're going to be using in this lab, where the drag goes in the opposite direction of the motion of an object. And it's also the scale of the object's speed squared. So we can see that it is negative b v squared times v hat, where b is the constant of drag. And we're gonna first look at a free body diagram for this system just to like be able to review this. The system we can see is the point mass at the red dot, which is the bottom part of the slinky, and we can see the tension as the blue arrow going up and the gravity as the green arrow going down. We can see they have the same magnitude, so we can kind of predict what will happen just using this free body diagram. So we'll quickly look at a tracker video, tracking. So at the start, you can see that it remains constant until it suddenly starts falling once that top hits the bottom. So as I was creating the glow script model, we have the initial conditions right here where we found the mass of the ball. We found the position relative to the height of the dude, as well as the velocity, which starts at zero. And then there is the change in time, the gravity constant, and there's also the proportionality constant for drag force uh, calculated with trial and error. And here are the iterations. So before the bottom fell, which is around before 2 seconds, that is when the net force on the bottom equals zero. So using these equations, we're able to calculate the net force and then also apply the momentum principle to calculate the exact location and velocity. And then after the bottom fell, we could see that the tension immediately goes to zero. So the net force is now not zero, it is drag force plus weight force. So this is after time is greater than 2 but less than 3. And that very short time, we can see we use this drag equation now into the net force, so that the net force actually has a value. So the dot actually moves by the velocity equation, and the position actually changes because of there is acceleration in the object. So you can see this is the glow script model, positions versus time. At the start, it is very constant, and then it suddenly falls. And we can see just off this that it is very similar to the tracker video that we caught. So we could see that we put it on top of each other, with the tracker video being the blue one and the red line being the glow script model. And we can see that it is fairly close. There are some differences due to some of the potential errors that I will talk about in the next slide. So some potential sources of error. The first one is the drag coefficient isn't completely accurate because of the trial and error aspect of it not being accurate, and then the slow motion aspect of the video. Also, the spring is not perfectly straight in the Y direction in the video. It's slightly tilted, and the slinky may be non-ideal because it may be worn out. So it might it's a spring constant and stuff like that may be slightly different in real life. Finally, what does it mean? So we could see the F tension is the blue, the F force and gravity is the green. In the end, what this means is that when going up and going down are equal, when the force tension and the force gravity are equal, basically the bottom won't move. So in the end, this is like magic because the top is moving, but the bottom doesn't move down until the top hits it, completely getting rid of tension and making the gravity overpower it. Thank you.